All right, let's talk about something that feels like pure magic in the world of programming. How can a system find one single piece of information buried in millions or even billions of others in what feels like an instant? Today, we are pulling back the curtain on the data structures that make this possible: hash maps and hash sets.
I mean, seriously, think about it. It's the absolute dream for anyone who writes code. You don't want to sift through a massive list, one item at a time. You just want to ask for something and get it back right now. This isn't science fiction. It's just really, really clever computer science.
And this is the promise. You'll see this everywhere. It's called constant time. And what it means is that it doesn't matter if you have 10 items or 10 billion items. The time it takes to find the one you're looking for stays, on average, the exact same. It's incredible. But how?
So, how on earth is that promise of constant time even possible? Well, the secret isn't some complex sorcery. It's actually a beautifully simple organizational system, and it's the foundation for both hash maps and hash sets.
To get our heads around this, let's use a simple analogy. Just picture a giant wall, lined with a row of numbered mailboxes. Now, instead of opening every single box to find your mail, what if you had a system that could tell you, instantly, the exact mailbox number where your mail is waiting? That's the big idea right there.
Here's how this magic mailbox system works. It's really just 3 simple steps. First, you have an item you want to store. We'll call it a key. Second, a special calculator, called a hash function, takes that key and, boom, it instantly spits out a mailbox number for it. And third, you just walk over and put your item directly into that specific mailbox. No searching involved.
And that whole system, that brilliant setup, that's what we formally call a hash table. It is the engine that drives everything. In computer science terms, the mailboxes are called buckets, and that hash function maps our keys to an index in an array. It's this direct mapping that gives us that mind-blowing, near-instant speed.
Okay, so if both hash maps and hash sets are built on this same awesome hash table foundation, then what's the difference? Why do we even have 2 of them? Well, it all comes down to a really simple question. What are you actually putting inside each mailbox? And this right here is the absolute core of it. A hash map stores 2 things, a key and then a value that's associated with it. You can think of it like putting a letter that has actual content inside the mailbox. A hash set, though, is much simpler. It only stores the key itself. It's just about presence. Is there a letter at this address or not? Yes or no? That's all it cares about. Honestly, this is the golden rule. If you can remember this one thing, you're 90% of the way there. If your only question is, hey, is this thing in my collection? Then you want a set. But if you need to store information about that thing, like a user's ID that points to all their profile information, then you absolutely need a map.
Okay, theory is great, but let's get practical. How does this actually play out in the real world? Knowing when to use which is what separates the pros, especially when you're in a coding interview or building a real project.
So, you're going to reach for a hash set anytime your primary question is about existence or uniqueness. Need to get rid of all the duplicates in a list? A set does that for you automatically. Trying to solve a maze and need to keep track of the paths you've already visited? A set is perfect for that.
And you'll use a hash map whenever you need to connect one piece of data to another. Want to count how many times each word appears in a book? Classic hash map problem. Need to store a product's ID and link it to its price and description? Yep, that's a map. It's all about creating that link between a key and its value.
So, at this point, this whole thing sounds a little too good to be true, doesn't it? Instant lookups all the time? Well, like with most things in life and in engineering, there's a bit of fine print. That amazing O1 performance, that's the average case, not a 100% guarantee.
And that leads us to the critical question every good developer has to ask. Is it really constant time every single time? The honest answer is no. And understanding why is what really shows you have a deep understanding of how this stuff works.
The catch is something we call a collision. What happens when your hash function calculates the exact same mailbox number for 2 completely different keys? Well, they have to share. What usually happens is they form a little list inside that one mailbox. And now, to find your item, you have to search through that little list.
To keep this under control, we track a metric called the load factor. It's a really simple idea. It's just the number of items you have stored divided by the number of mailboxes available. Think of it like how crowded the system is. If this number gets too high, our mailboxes get too full, and performance starts to take a hit.
This table tells the whole story. On average, if you have a good hash function and you keep that load factor low, you get that beautiful O of 1 speed we love. But in the worst-case scenario, performance can completely fall apart, down to O of n.
At that point, you're just searching through a list, and you've lost all the magic.
So when does that worst-case nightmare happen? It's usually when you have a poorly designed hash function that isn't spreading things out evenly, or you just get really unlucky with your keys and they all happen to map to the exact same mailbox. It becomes one giant traffic jam in a single bucket.
Now, for anyone prepping for interviews, pay attention because these are gold. First, never use something that can change, like a list, as a key. It'll break everything. Second, remember the hash equality contract. If two objects are considered equal, their hash codes must be the same. And always be ready to talk about the load factor and the fact that most hash tables don't care about the order you put things in.
So how do we stay in that happy O1 world? We actively manage the load factor. When the table starts to get too crowded, most implementations will automatically do something called resizing. They basically build a bigger wall of mailboxes and resort all the existing items into the new, larger space. That's the secret sauce that keeps things running fast.
So, there you have it. You now know when to reach for a hash map versus a hash set, and you understand the critical performance details that go with them. But you might have noticed we keep talking about a good hash function. That leaves us with one final, fascinating question. What actually makes a hash function good? Well, that's a deep topic for another time.